Hi everyone, welcome back to Food for Thought Physics, where today we're going to be analyzing this neat little configuration known as the Atwood machine, or rather the idealized version of this Atwood machine. The Atwood machine is going to consist of a pulley, which is for our purposes is going to be massless, as this is the ideal case, and there's going to be some massless rope that wraps around this pulley, and this rope is going to be connected to two boxes or two objects really that do have mass. We're going to have a smaller object, or a lighter object over here rather, which has mass small m, and a heavier or a more massive object over here, which is going to have mass big M. And we're going to try to solve for the accelerations of these objects. So first of all, it should be kind of clear that the larger block is going to be accelerating downward with some acceleration a, and the smaller block is going to be accelerating upward with the same magnitude of acceleration a. And here we're actually going to do something kind of neat. We're going to set our single axis, our single coordinate axis as a x-axis that wraps around the pulley, where this direction is going to be the positive x-axis. And the reason we can make this axis wrap around is because that way we're going to have that both accelerations are actually in the same direction, as over here the axis does go up and over here the axis points down. And they're both going to be in this positive x direction. So now let's start on our free body diagram. As always, we're going to, first of all, on this larger block, we're going to have some force of gravity going down. That's going to be a big mg, just regular force of gravity. We're going to have a force going up. That's going to be the force of tension on this big block here. Remember, tension is going to occur because this rope is going to be resisting being stretched, which means it's going to pull in on itself. And we're going to call this tension 1 for now. Now for the smaller block, we're going to have some gravitational force, small mg, pulling down. And again, some tension pulling up again, this time because the tension, remember, is always going to pull towards the center of the rope. And let's call this tension over here tension 2, T sub 2. And well, what other forces act on this rope? We might think, well, none. Well, assuming that, of course, that the rope either is going to slide frictionlessly along the pulley, or that it's wrapped tightly around the pulley, and the pulley is just going to rotate without any resistance as it's massless. So either of these cases actually correspond with the idealized case. We just need no other forces to act on this rope. Now, if the pulley had mass, or if the pulley has friction against the rope, that's going to be a very different case. But here we only care about the idealized case, so we're just going to say that there's no other forces on this rope. Now, if you remember from the other tension analysis we did, well, we see since this rope is massless, the net force must be 0, because we're going to have m times a must be 0, as the mass is 0. So the net force must also be 0. And since this T1 here is going in the negative x direction, while T2 is going in the positive x direction, that means that implies that T1 must equal T2. In order for the net force on this rope to be 0. So instead of writing T1 and T2, we can just refer to these as both some constant T, some tension T. We can now apply Newton's law to both boxes. The bigger box is going to be some net force, big MA, is going to equal big MG minus T. Again, we're not going to refer to T1 and T2 anymore. It can just be some T that's the same on both sides. And what we see again, this big mg is going to go in the positive x direction, while this tension is going in the negative x direction. For the small block, it's reversed. In this case, for this small ma, we're going to have that the tension is actually going in the positive x direction this time, while the gravity is going to be going in the negative x direction. So it's going to be ma equals t minus small mg, rather. Now we have a system of two equations. We assume, of course, that m and g, both m's and g are all known. What we don't know is t and a. So we have two equations, two linear equations actually, and two unknowns. So we have a system of equations that we should be able to solve. And thankfully for us, this system is very easy to solve. We simply add both of these equations together, and we eliminate the t's immediately. And this gives us big M plus small m times a, after factoring the big M and small m, since we get big MA plus small ma. This is going to equal now, the t's cancel, so we just get Now we get, well, big mg minus small mg. Again, we can factor g out, and we just get big M minus small m times g. And if we want to solve for a, this is now trivial. We divide on both sides by the sum of the masses, and we get that the acceleration is equal to big M minus small m over big M plus small m, all multiplied by g.